Good morning, everybody. Here we are, ready to start the day. We're judging by when you guys are handing things in, ready to welcome the vampires back into the world. You guys are nuts. Anyway, here's the deal. Today we are going to talk about how we measure pH, and it's going to be the last thing we talk about for this whole chapter. That's right, we're wrapping up the old acid and base chapter. So, last time we were talking about titrations, right? Which is where you take a known acid or base. We know the concentration very well, and we add it to an unknown, and that way we can tell how acidic or basic that unknown was, right? And we said, like, okay, we'll use like this indicator and that indicator, and once it's neutral, everything's great. And it's like, man, how do we know if it's neutral? Like what is the measuring scale? There's got to be some way that we measure what is acid, what is basic, or what is alkaline, and what is neutral, and that's the pH scale, and that's what we're digging into today. But first, before I dig in too far, what I want to talk to you guys about is the homework. There are a lot of people who are asking questions about the homework, like, Stu, how do I do this one? Stu, how do I do that one? How do I know how I'm doing? So what I'm going to be doing is I'm going to be posting the answer keys to the homework onto the Google Classroom so everybody can look at it. We can go over things because despite the fact that there is no Regents, I am not terribly broken up about that. There is still going to be a final exam. So we still need to learn the stuff. We still need to dig into it. We still got to get it in our heads because there is a final exam at the end of the year. So, yeah, once I post the answer keys, no more homework is going to be accepted, just like when we were in class, right? I'd walk around, I'd check homework, we'd go over homework, we'd go over questions and figure stuff out, and then we would move on. If you didn't have the homework done, you didn't have the homework done. We're all big boys and girls. It's water on the bridge. We do better next time. That's how we do. So that's how we're going to do here because, man, a lot of people got pretty far behind, and we're just not going to let that happen anymore because we're in the fourth marking period. Final stretch here, guys. And there is still a final exam to get ready for. So, that all being said, let's dig into pH scale. Right, so acidity and alkalinity. This word right here, alkalinity, this is like what we mean when we say basicness. It's like another word for how basic something is. It's like same thing, two different words. One's old-fashioned, one's a little more modern. Does it really matter? No, they're just interchangeable. So today what we're going to look at is how do we measure how acidic or how basic or alkaline something is. And before we do that, we have to remember this. In pure water, like the purest H2O, we will still have some hydrogen ions. We will still have some hydroxide ions. And one thing I want you to get used to seeing is you see this little brackety thing here? These brackets are the symbol for concentration. So what this is actually saying is the concentration of hydroxide or hydrogen and the concentration of hydroxide are equal. So these are at equal concentrations in pure water, right? The only reason these are equal is because it is absolutely pure water. And here's the thing I want you to dial into. See that exponent? They both have a concentration of 1 times 10 to the minus 7. This is a very, very, very small number. It is 0.000001. That's really, really small, right? It's a ridiculous number to try to write down. Like nobody's gonna be like 1, 2, 3, 4, 5, 6, 1. Nobody wants to write that. That's stupid. Like I don't ever want to have to deal with a number with that many zeros. You guys should know by now, I would not do well. So we had to come up with a scale to kind of deal with these really small numbers, and we did. It's called the pH scale. The pH scale is pretty awesome because there's this basic thing, which I should say for us, it's going to be really easy. Like some things are crazy hard. This time, man, this thing is going to be easy for y'all because the exponents always add up to 14. Always. Like, see, this concentration, the hydrogen ion is 1 times 10 to the minus 7. The hydroxide ion is 1 times 10 to the minus 7. So those exponents, minus 7 and minus 7, they always add up to minus 14. Always. which is delightful. You see, this is a state of equilibrium, right? So you guys see this little guy right here? It's a state of equilibrium. So what that means is, as this goes up, that has to go down. As this goes up, that has to go down. Because do you remember during this whole equilibrium thing, let's make something more acidic. So if we added a whole bunch of this stuff, right? So we pour it into this bucket, everything is going to flow this way, right? But every time it flows this way, it's going to grab a hydroxide and flow that way. We add another hydrogen ion, it grabs another hydroxide. We add another hydrogen ion, we grab another hydroxide. So as the amount of for this example, because we're adding a bunch, the amount of this is going to go up because we're adding it, and this one is going to go down because it's being used up in this equilibrium thing. What we need to know, really, what we have to know is this right here. They all add up to 14. There's like the base knowledge thing that you have to know. This is just the why. You know what I mean? I'm not so certain that's like the most epically important thing to have inside of our brain. But to measure this, like I said, we have the pH scale, and this tells us how acidic or how alkaline a solution is. It basically gives us the ratio of hydrogen to hydroxide. And we need to know that they are related, right? They are these two things here are stuck together. Whatever this one does, like if we mess with this one is going to be affected just as much, right? Because it's like they're all in the same like chemical equation equilibrium there. So here's the deal. The pH scale. It is used to tell us how alkaline or basic it is, and we have a range of 0 to 14. 0 is the lowest it will go, 14 is the highest it will go, and here is how we calculate it. We need to do a negative logarithmic function of our hydrogen ion concentration, because this is called the pH scale. We are going to use the concentration of the hydrogen. That's simple, right? Y'all ready for like log functions? But not just log functions, but negative logarithmic functions. Yeah. Don't worry, it's not that bad. We're gonna make it nice. We're gonna make it real nice for you. I am no Dean Fleming, dude. I am no dude. So we're gonna keep the math simple. Here's an example. In pure water, the concentration of our hydrogen ion is 1 times 10 to the minus 7. Right? Well, if we take a negative log of this number, guess what we end up with? We end up with 7. That's it, man. Read this. Be happy. That's as far as we're taking it. We're not going to go crazy with numbers and whatnot. I just want you to have a basic idea of like what the pH scale is even talking about. All you need to do is take the exponent of your concentration and make it into a whole number. That's it. That's all you got to do. Except, of course, there's more. Of course, there's more that you have to keep in mind. So here's the deal. 3 things are totally interrelated with each other. We have, the one thing is the pH. The other is the concentration of your hydrogen ion. And the third thing is the concentration of your hydroxide ion. Right? So these 2 things are locked. The pH and hydrogen ion concentration, they are locked into each other because one is like from the other. So if we're given a pH of 4, right? That means that my hydrogen ion concentration is 1 times 10 to the negative 4. Because remember, let's go back up here, right? If your pH is 7, that means that your exponent is minus 7. If your exponent is minus 7, it means that your pH is 7. You guys see how that works? All right, let's go back down to this one. So if my hydrogen ion concentration is 1 times 10 to the minus 7, how in the world could I possibly know what the concentration of the hydroxide? If hydrogen is 1 times 10 to the minus 7, hydroxide, there's nothing in. Watch. Let's go back up to this. See that? Did you remember this? See this right here? Remember, I was like, man, you got to remember that. Both exponents always add up to minus 14. Keep that in mind. Okay, here we are right back here. We know hydrogen is 1 times 10 to the minus 4. That means the hydroxide is going to be 1 times 10 to the minus. Say it. Say it with me. Say it out loud. I'm listening. Yeah, got it? Did you see how easy that is? These three things are all totally interlocked. The pH and the hydrogen ion scale, those are totally like the same thing. You just take the exponent, make it a positive number. That's it. If you have a positive number, make it a negative exponent. And then these two exponents here, they have to equal minus 14. That's it. That's as far as you need to go with the pH scale. Except for one other thing. But let's do a couple of practices here. Let's do rainbow pen. Okay, so if hydrogen is 1 times 10 to the if hydrogen is 1 times 10 to the minus 12, what is the hydroxide ion concentration? What is the pH? Well, man, we can do this. Remember, we have our like tower here of like interconnectedness. Pretend there's a little plus. All right, man. We know how these three things are related. So what are we given? We have this. We have the concentration of the hydrogen ion. And I'm going to go with something I can actually read. 1 times 10 to the minus 12. Well, we can go both ways here. I'm going to take this negative exponent, make it into a number. I'm going to take this minus 12, because they both add up to 14, right? See how it works? Nice. So what does that even mean? Like, what does a pH 12 mean? Like, is that acidic or is that basic? Well, actually, before we go too far, let's look at this really quick to get us ready for the next part. What is 1 times 10 to the minus 12? Oops. That's what 1 times 10 to the minus 12 looks like. 1 times 10 to the minus 2 looks like that. So which has a greater concentration here? Yeah, this has a much greater concentration. How I'm writing on stuff. Do you guys get what I'm saying? So this is what's important to see, is that like if your pH is 12, right? That doesn't mean that you're very basic. That indicates, I mean, look at these two numbers here. Look at this. That's teeny, man. That's like almost nothing. Look at this. That's like nothing. That's huge. I mean, in comparison here. So if you have a big pH number, that means, remember, because that's the exponent. That's the negative exponent. That means that the hydrogen ions are like so small compared to the hydroxide. Do you guys get what I'm saying? So what this means is if you have a very large pH, it's very alkaline. It's not acidic at all. It's way stronger on the alkaline side, or basic. It's very basic. You guys follow? That is important to understand how the pH scale works. Because changes in pH are not like incremental. It's not like stepwise. It's because these are exponents. It's like it's a logarithmic change. Exponential, if you will. All right, so look, because the pH represents a power of 10, an exponent. This is so important to know, man. That's an exponent that we're talking about. Each change in pH number indicates a 10 times increase, or a 10-fold increase or decrease in the hydrogen ion concentration. So the difference between pH of 7 and 6 is not 1, it's 10 times. So that means that, like, if here, let's come down here. If 7 is neutral, right? If we come down to 6, 6 is 10 times more acidic. If we went to pH of 8, This is 10 times more basic, or 10 times less acidic. You guys understand what I'm saying here? Right. So here we go. This is kind of what I was talking about up here when I was like writing out the exponents. Like the reason I did this is to help explain this. So a pH of zero, this is very, very acidic. Why? Because the hydrogen ion concentration is 1 times 10 to the 0, right? pH of 0, which gives us a concentration of 1 molar for the hydrogen. And that means that the hydroxide is going to have to be 1 times 10 to the minus 14. I don't have enough space here to write that out. So that's going to be very, very small. Very, very small. So this will be, that means that there's a huge concentration of hydrogen as compared to hydroxide. Very, very acidic. Neutral, the exponents are both going to be exactly the same at 7. And over here, where we have a pH of 14, that means that the hydrogen ion concentration is 1 times 10 to the minus 14. That's very small concentration. And that means here that the hydroxide ion is 1 molar. That's pretty high. And remember, it's comparing these two things. It's the ratio of these two things that make it really acidic or really basic. So that's why when you have a pH number that's very big, it's not acidic at all. It is actually very, very, very basic. If you have a number that's very, very small, that's really, really acidic because that's the exponent. The alkalinity is like in the basement. Got it? Be good here? Awesome. So let's check it out. Let's check out the differences here. Who color dots do? I don't even know. Let's just do black. Okay. So if we go from pH 7 to pH 6, there's two ways that we can describe this. This is 10 times more, acidic, or 10 times less basic, right? Because we're moving away from alkalinity, right? 10 times. Let's do the next one. Going from a pH of 3 to a pH of 10. Hold on a second. 3, 4, 5, 6, 7, 8, 9, 10. I'm going to need to write that down. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 100,000 million. 100 million times more basic. This is a 1, 2, 3, 4, 5, 6. Oops, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7. Oh shoot! I need to get rid of one of those things. Let's see if this eraser actually works yet. Oh, it does. Oop, look at that. I don't know what just happened there. Sorry, man. I got that all mixed up. This is hard. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, there we go. More basic. That's a lot. Or whatever that is. Fold bigger times more basic. I don't know. They have so many different ways of saying it. Let's go to an easier one. 8 to 5. 8, 5, 5, 6, 7, 8. That's 1. 1,000 times more. Okay, so we're going from 8 to 5. That means we're lowering the pH, more acidic. You guys get what I'm saying? Yeah, I should have chosen something with 7 zeros. Dyslexia and 7 zeros does not work well. Oh man. You ever wonder how you survive? Same here. I have no idea how I get through my day, but I do. So anyway, you guys get how the pH scale works? One step is 10 times. One step is 10 times because, again, the pH is an exponent. It is not just one step more. You know, Like molarity, if it's 1 molar or 2 molar, it's just 1 molar more. It's not like that with the pH. It is a 10-fold, a 10 times more acidic or basic every time you change the pH number by 1. So next thing you must ask is, how do we measure the pH? Simple. For us, like, we're not going to use pH meters because they can get weird and complicated. We're just going to use pH indicators, which is super easy. It's just like stuff that you squirt into water and they change color with different pHs. So different indicators change at different pH values, and we just choose one that works using table M. Boom, right here, table M. So look, here's how this whole thing works. So let's look at like methyl orange really quick. Okay, methyl orange, this is the approximate pH color change, and right over here, this is the color change. So what this means is, if you have a pH over here, like 0 to 3, it's on the, that means that the pH is on the left. That means you're gonna have a color that's on the left, so it'll be red. So if you took methyl orange and you put it into a solution with a pH of 2, it would look red. Does that make sense? If you took methyl orange and you put it into a solution that had a pH of 4.5 all the way up to 14, that's on the right hand side. It'll be the color on the right hand side. It'll be yellow. Does that make sense? Now you might ask, what if it's right in between the range? Like, what if it's right in the middle? What if it's like 3.5 or 4 or something in between? Well, then you have something in between these two colors, and this is where, like, you wish you knew your art stuff and your colors. Because what is red and yellow? Orange. Yeah. So if you have between 3.1 and 4.4, this will be orange. So from 0 up to 3, it's red. 3.1 to 4.4, it's orange. 4.5 and up, it'll be yellow. You dig? Bromethymol blue. They all work the same exact way. From 0 to 5.9, it will be yellow because that's on the left. If it's 6.0 to 7.6, yellow and blue makes green. So right within the range here, it'll be green. If it's 7.7 and up, it'll be blue. And that's how it go. You guys dig what I'm saying? Lovely. Let's move on, or back to our thing here. Table M. All right. So here's like an example of how it works. Bromethymol blue is yellow. Okay. Here's the situation here. So bromethymol blue. Okay. So let's do this one, thymol blue. If it is yellow, all right, do you see how yellow is on the left-hand side here? So that means it has to be below 6. Does that make sense? Let's see if we can do this. Oop. I chose the wrong one. I'm a moron. Hey guys, I totally messed up. I feel silly now. That's okay, I'm gonna get right over it. Everybody makes mistakes. Thymol blue. Not bromethymol blue, thymol blue. Okay, so here, where are we? Thymol blue is yellow. This is going to be bad because I'm using green. So if it's yellow, it's going to be on the left, so it has to be below 8. Okay, let's see if that worked. Oh yeah, look, it's going to be less than 8. Nice. Let's do the next one. Brome cresol green. Oh boy, brome cresol green. So this is what I'm looking at now. Is blue. So it's going to be on the right. So it has to be 5.4 and up. Okay, let's see if we're right. It's got to be above 5.4. So what does this tell us? There's your pH range. It has to be between 5.4 and 8.0. It's not a perfect situation when we use indicators, but it works. It works well for almost all of our things that we need. And if not, then we use a pH meter. But we don't need it. You and I will not need to do that in our particular situation. So let's go on to the next one. If a solution has a concentration of hydrogen ions that is 1 × 10⁻⁵ molar, what color will the following indicators be? Okay, so first thing I'm going to need to do is figure out what the pH is, and oops, what's going on? Okay, so my pH, because we're not going to be able to answer this if we don't have our pH. Our pH is 5. All right, so in this case, bromethymol blue. Let's come up here to see what bromethymol blue will look like. Bromethymol blue. Oh, okay, that's going to be yellow. Ooh, you know what? Let's do this. Let's see what color methyl orange will be. Methyl orange. Methyl orange is going to be yellow. Even though it's, nice. And what color will bromcresol green be? Remember, we're with a pH of 5. So let's come up here and check out bromcresol green. Bromcresol green. Ooh. It's not 3 point. It's going to be it's going to be right in the in between these things, right? So what is yellow and blue? Yellow and blue, you bet, make green. See how that works? That's how indicators work. Easy peasy lemon squeezy. Look at that. We made it to the end of yet another amazing learning adventure together. And what I would love for you guys to do also we made it to the end of a chapter, so what I would love for you guys to do is do this one, interpreting pH. This one is the whole homework is going to be based on, let me scroll up, on problems just like this one and this one. Okay, that's if you were able to follow along with this problem, you're going to be golden. You need to take the hydrogen ion concentration, figure out the pH, and figure out the OH concentration. And now it will be a little more difficult though. Like for example, what if they said, what if they gave you the OH concentration is 1 × 10. I don't know. I'm going to make something up. 1 × 10⁻⁻10. Right? Well, we know what the hydrogen ion concentration is going to be. Right? Because both of the exponents have to add up to 14, so this will be 1 × 10⁻⁴. And if we know the hydrogen ion concentration, we know that the pH is going to be equal to 4. Yeah? Super sweet, super easy. So that's what the first homework is going to be like. The second one, a little bit different, multiple choicey, and that one you're going to need to use the reference table. This guy right here, you're going to need to use your table M with your indicators, so you know what color things will be. Just remember, if the pH is off to the left of the range, it'll be the color on the left. If the pH is right in between the range, it'll be both of those colors put together. And if the pH is all the way out to the right, then it means that it'll be the color that's off to the right. Got it? Awesome sauce. Thanks for hanging through with me. I will be back again for another installment of learning. But until then, you guys take care of yourselves, be safe, and wash your hands, man.